go over sorting algorithms. First, I'll cover some properties of these sorting algorithms. So first, what does it mean for a sorting algorithm to be in place? Well, that just means that the algorithm does not use any extra space. So if an algorithm is not in place, that means it'll use an extra array. So what does it mean for a sorting algorithm to be stable? Well, that means that from the unsorted to sorted array, it's stable if the relative order of the equal keys is preserved. So if you look at this array here, it's unsorted, and it has two equal keys, these twos right here. And if the algorithm sorts the array and the green 2 is still before the blue 2, that means it's stable. But if it sorts the array and then now the blue 2 is in front of the green 2, that means the algorithm is not stable. So we see the relative order of these 2's on this left array is preserved because the blue 2 started before the green 2, and after the array was sorted, it's still after the green 2. Okay, so now I'll talk about selection sort. So for selection sort, it's essentially you start from the first index, and then for each index, you look at the rest of the array to see, to find the minimum element, and then you swap it. So first, we can look at this first index, and then we see, okay, from this part of the array, what is the minimum element? It's 9. So I can take 9 and swap it with the element here. So I swap and put 9 here, and then I'll still keep this red. Yeah, right here. Okay, and then now we know 9 is here, so then we look at the second index, and we see for this index, which of the elements in this part of the array is the smallest? Well, we see that the smallest is 11, but 11 is already in this index, so we don't really have to swap anything. So we can just keep it here, and I'll change it to be green, so we know that these two have already been looped through. And I'll do one more iteration. So now we're looking at 64. So we see, okay, for 64, which element in this part of the array is the minimum? And we see, okay, 11 is the minimum. So I'm going to swap 11 with 64. So let me just put it here. And then, okay. So, and essentially we'll do that for every element in the array until the entire array is sorted. So if we want to think about the complexity of selection sort, we'll see, okay, we have to loop through each element in the array, and then for each element we have to find the minimum element. So we see, so since we loop through each element, it's O of n here, but also when we find the minimum element, it also is, it's like O of n. Yeah. So we have like two nested loops. So the worst case would be O of n squared. Right. So the worst case complexity of selection sort is O of n squared. So now let's quickly look at some loop invariants for selection sort. So the simplest loop invariant is that index I is less than or equal to high and it's greater than or equal to low, which means that I is greater than or equal to the lowest index, which is usually going to be 0, and it's less than or equal to the highest index, which is usually the length of the array. And then another loop invariant is sorted, which states that between the lowest index and the index that you're currently looking at, the array is sorted. So if you look at this array here that we were doing selection sort on, currently index I would be here because we're looking at this part of the array right now. But we know that all the elements before this section of the array is already sorted. So that's just what this loop invariant says. And the final loop invariant is less than or equal to segments, which basically says that for the segment low to index I, all the elements in this segment will be less than or equal to all the elements from the segment I to high. So this just says that if this was index I, all the elements in this part of the array will be less than or equal to all of the elements in this part of the array, which kind of makes sense because for a selection sort, we take like the minimum elements and we swap them over to the left side. And then for selection sort, we know that the sort is not stable. And this is because the swapping, it doesn't really, you kind of swap sort of randomly. You don't really care about preserving the relative order per se. So if you look here, I have two 11s and I drew them kind of weirdly. So if you go back in the video, you see that this 11 with the fancy ones was to the left of this 11. But as we did selection sort, it ended up at the right. This 11 ended up at the right of this 11, which basically goes to show that selection sort is not stable. But luckily, selection sort is in place because we didn't need any extra memory to perform a selection sort.